Hello everyone and welcome again, and thank you for joining us on today's webinar, Reducing Ammonia Costs with NOx Scrubbing. I'm Allison Sterling, Marketing Manager at Emerson Micromotion, and I'm pleased to welcome you to our Emerson Flow Expert webinar series. Before we begin today, I'd like to take a moment to acquaint you with your webinar environment. On your screen, you should see a presentation window on the left side, a Q&A chat window in the upper right-hand corner, media player controls, and a resource box with related content that you can view and download during the webinar. You can resize, move, or minimize any of these windows during the event to fit your viewing preferences. At the bottom of your display, you can see a row of icons that give you some added capabilities, like sharing this webinar via social media channels or requesting a visit with one of our flow experts. Throughout our presentation, we encourage you to interact with our speaker by typing in questions and comments using the chat panel. We will be answering questions at the end of the event, and we are also going to be recording today's webinar, and we will make a link to the recording available to you 24 hours post-event via email. On today's webinar, we are lucky enough to have joining us Marty McDonough. Marty is the North America Power Industry Business Development Manager for Emerson Flow. Marty has been with Emerson for the past 12 years in sales and business development roles. He enjoys spending time with his family and going to professional sporting events like the NFL. Welcome, Marty.
Thank you, Allison, and welcome, everyone. We are excited to have you here with us today. Like Allison said, my name is Marty McDonough, and I have the privilege of visiting power generation companies around the country. With this, I've noticed there are some themes that are universal as far as industry challenges. The top two, as shown in this Black & Veatch study, include concerns over improving plant reliability and increasing environmental regulation, which fall into today's webinar. During this webinar, we are going to discuss how new developments in smart instrumentation can improve the reliability of your NOx emissions equipment and assure that your plant is compliant in a cost-effective manner. As the cost and complexity of environmental compliance continue to rise, power plants are turning to a new generation of instrumentation to improve reliability and reduce calibration frequency. The trends show us that environmental regulations will only get more complicated, so managing your assets in the most efficient manner will maximize availability and profitability. At this point, I'd like to ask a quick poll question to the audience. That question is, what flow technologies do you use in and around your SCR unit? I'll give you a few seconds to pick. Great, thanks. With that, let's discuss our next topic, which leads us to flow technology trends and advancements in the industry. Let's start by taking a look at this chart of precision flow measurement technologies. As you can see, Coriolis meters are one of the fastest growing flow technologies in today's marketplace. Traditional flow measurement technologies, such as differential pressure, have a large market share, but are not growing at the rate that Coriolis meters are. Let's take a look at how Coriolis technology works to see why. Let's start by looking at how Coriolis meters measure mass flow. All of our meters work in a similar way. The material to be measured enters the meter through the process connections and passes through a flow splitter that divides the material equally between the measurement tubes. 100% of the material passes through the measurement tubes. There is no slipstream inside the meter. The manifold and end connections of the meter provide a rigid structure to mount in your pipeline while isolating the measurement sections of the meter from any outside noise. The meter tubes are vibrated at their natural frequency with a low voltage DC drive coil that you can see mounted to the tubes in the top cutaway. With no flow, the meter tubes vibrate like you see here in the top diagram. The flow moving through the tubes tries to continue on its path perpendicular to the axis of vibration, resisting the movement. That resistance to the movement causes a deflection of the tubes in the form of tube twist. The tube twist, or angle of deflection from the vibration plane, is measured and converted into a mass flow measurement. When there is flow, the Coriolis effect on the tubes twists like what you see here in the bottom diagram. We measure that tube twist with magnet and coil assemblies called pickoffs. They are mounted to the flow tubes as seen in that bottom cutaway. As each coil moves through the magnetic field of the adjacent magnet, it creates a voltage in the form of a sine wave. So to summarize, during a no-flow condition, there is no Coriolis effect, and the sine waves are in phase with each other, as illustrated in the meter at the left. When fluid is moving through the sensor tubes, as shown on the right, Coriolis forces are induced, causing the flow tubes to twist in opposition to each other. That time difference between the sine waves is measured is called delta T, or time delay, which is directly proportional to the mass flow rate. The measurement of mass flow is very simple, as is the calibration. The flow calibration number consists of 10 characters, including 2 decimal points. The first 5 digits are the flow calibration factor. This calibration factor, multiplied by a given delta T, yields mass flow rate in grams per second. So if a user wanted to shift the calibration by, let's say, 2%, simple 2% change in the calibration factor could be made. The last 3 digits of the calibration number are a temperature coefficient for the sensor tube material. This coefficient compensates for the effect of temperature on tube rigidity, or Young's modulus of elasticity. It is a percentage change in rigidity per 100 degrees C. The 4.74 number shown here is for stainless steel. A different number would be used for other metallurgies like Hastelloy or titanium. The RTD that measures the tube temperature is plus or minus 1 degree C from the process temperature and can be configured as an output variable as well. Let's now look at how we measure density. Density measurement is based on the natural frequency of the system, including the flow tubes and the process fluid. As the mass increases, the natural frequency of the system decreases, and as the mass decreases, the natural frequency of the system increases. Frequency is measured in cycles per second, since it's easier to time the cycles than to count them. The micromotion transmitter computes density of a process fluid by using 2 period, the number of microseconds per cycle. 2 period is inversely related to frequency, therefore density is directly related to 2 period. Density calibration is performed at the factory on air and water. Meters are filled with air, resulting in a 2 period of 10,484 microseconds in this example on the slide. Next, the meter is filled with water, which results in a 2 period of 10,966 microseconds. These 2 values, which are called K1 and K2, are plotted against the density of the 2 fluids the meter is calibrated on, in this case, air and water. D1 is the density of air, and D2 is the density of water. The transmitter stores these values and automatically calculates the fluid density based on the measured 2 period. In other words, if the 2 period is 10,817 microseconds, as the example shows above, then the transmitter knows that the fluid density must be 0.6871 grams per cc to a high degree of accuracy. Micromotion meters can perform as good as plus or minus 0.002 grams per cc on density measurement. Micromotion performs the initial density calibration in the factory. Field calibrations can also be performed using air, water, or virtually any process fluid with a known density. As you can see on this slide, an increase in temperature decreases the density and results in an increased volume. Therefore, the higher the temperature of a fluid, the greater volume it will occupy. Notice how the units of mass stayed the same when temperature went up. This is because mass does not change with temperature. The bucket on the left and the bucket on the right still have the same mass, even though their temperatures and volumes are different. If you were buying gas for your car by the gallon, do you want to buy the gallons at 16 degrees or at 94 degrees? I'd want to buy at 16 degrees because I would get more mass of gas for my money. But if you were paying by the pound, you would pay the same regardless of temperature. This is a significant reason why custody transfer with Coriolis meters is so successful. The same principle applies with pressure, as shown on the right, mainly when talking about a gas. As pressure changes, so do density and volume, but mass stay the same. Now let's talk about some of the reasons why the use of Coriolis technology has been growing. First, its direct mass measurement, as previously discussed, as well as its high accuracy for both mass flow and density. 0.05% of mass flow rate, and plus or minus 0002 grams per cc on density. Coriolis meters also have very large accuracy turn down, no moving parts, therefore no maintenance, easy installation and startup, multivariable measurement, meaning flow density and temperature out of one device, no flow conditioning or straight run piping is required, and last, the water calibration transfers to other fluids, which keep calibration simple and its cost low. From a micromotion and Rosemont flow standpoint, Emerson has a very broad portfolio of products, from our elite high-performance products that are certified for physical custody transfer, all the way down to our R-Series Coriolis meters and our utility-grade vortex and magnetic flow meters. Now let's look closer at the selective catalytic reduction process. Selective catalytic reduction is a means of converting nitrogen oxides, also referred to as NOx, with the aid of a catalyst into nitrogen gas and water. A gaseous reductant, typically anhydrous or aqueous ammonia or urea, is added to a stream of flue or exhaust gas and is passed through a catalyst bed. Some of the challenges facing users of SCR technology are making sure that the ratio of reductant to catalyst is correct for the amount of flue gas being scrubbed. Since the stoichiometry or chemistry is based on mass or mole weight reactions and not volume, it is better to control using a direct mass measurement. Coriolis meters can help with mass balancing, precise mass flow measurement, reducing ammonia slip, and measuring the ammonia concentration, all in one device. In addition, due to their design, they contain no moving parts that can improve unit reliability as well. Safety concerns are one of the primary drivers in SCR system design and selection. Ammonia characteristics shown above show why this is the case. At 150 to 200 ppm, we start with general discomfort, moving to 2000 ppm and up, which could be fatal. Let's start to look at different systems and reductants used. Anhydrous ammonia is one and is listed by OSHA as a hazardous substance. It requires a risk management plan and special permitting. Here we show an anhydrous ammonia system. Accurate flow measurement of the anhydrous ammonia vapor going to the injection grid is important to assure that the ratio of reagent to catalyst in the SCR unit is correct. Under-injection will not provide sufficient NOx scrubbing, while over-injection leads to ammonia slip. Both can lead to emission violations. Next, we have aqueous ammonia. Typical dilution concentrations in the U.S. are 19 and 29%. It is considered much safer than anhydrous, but still listed as hazardous. Here we have an aqueous ammonia system. Precise flow measurement of the aqueous ammonia going to the ejection grid is important to assure that the ratio of reagent to catalyst in the SCR unit is correct. Once again, under-injection will not provide sufficient NOx scrubbing, while over-injection leads to ammonia slip. Some added possible consequences of ammonia slip are: when over-titrated ammonia escapes and it wastes money, it can violate permit limits, as we mentioned earlier. With high sulfur fueled ammonium sulfate and bisulfate form, which can foul downstream equipment, and ammonia can contaminate fly ash, making it hazardous. Last, we have urea. Safety is the principal advantage of a urea-based ammonia system. Urea is non-toxic and not regulated by DOT. In a urea to ammonia system, as shown here, mass flow meters are used on the inlet and outlet of the hydrolyzer for mass balancing, as well as on the ammonia vapor injection for the SCR process. Once again, the precise flow measurement of that ammonia vapor is critical because it assures the proper ratios, avoiding under as well as over injection. Micromotion Coriolis meters are uniquely situated to act as pay and check meters in your ammonia receiving area. By measuring direct mass flow, they verify the amount purchased as well as the received concentration. They're an excellent insurance policy to assure that you get what you are paying for from your ammonia suppliers. At this point, I'd like to take another quick survey of the audience. The two questions that I have are there accounting inconsistencies in the amount of ammonia that is purchased versus used in the plant? We are finding that end users have started to look here for possible savings opportunities and are engaged on a couple of these studies at the moment. Thank you. The next question is, does your plant ever suffer from ammonia slip in your SCR system? Emerson has a broad portfolio of possible solutions for this from a host of business units, including Power and Water Solutions. Please reach out to one of us. We would love to help. Let's now look at Emerson's solution that can help save on calibration costs and provide even more reliability in your system. It's called Smart Meter Verification, or SMV. Coriolis meters have very good long-term stability and can reduce or eliminate unnecessary calibrations in many applications. The above graph details multiple proving events of a Coriolis meter and a positive displacement meter. You can see the reliability and repeatability of the Coriolis meter. Even with Coriolis's measurement stability, sometimes when a measurement is important, such as for fiscal custody transfer, safety, or critical process control, you want the confidence to know your flow measurement is reading correct. Emerson is focused on delivering that with Smart Meter Verification. There are various people in the plant that interface with our flow meters, from maintenance and engineering to environmental health and safety personnel. Many different areas of the plant can benefit from Smart Meter Verification. At this point, I would like to show a short video on what SMV is and its potential benefits within your plant.
Hi, today we're going to talk about Emerson's micromotion and Smart Meter Verification. This is Tom. Tom is a reliability engineer. His job requires him to coordinate with everyone at his plant and keep the plant running smoothly. Tom knows that his Coriolis meters are reliable. He knows that they're safe, and he knows they're accurate. But how does he prove it? Well, the way Tom proves it is harder than it should be. His applications call for proving meter accuracy at regular intervals. But pulling meters to be drained, cleaned, and shipped to a lab means Tom has to interrupt his process and reduce production. In addition, removing meters increases the risks of damage during transit, and there's no guarantee the meter's performance will improve. To combat that, there have been pretty inventive ways to verify and calibrate meters on-site or in the lab, like catch and weigh tests done with a bucket on a scale, the use of master meters and portable provers, or even gauging the tank level against an old strapping table. When you're trying to calibrate a meter with 0.1% accuracy, these techniques might not stand up to an audit. Last year alone, Tom and his team spent $300,000 performing calibration checks just to prove something that Tom already knew. The meters hadn't changed. Micromotion has a better way. We call it Smart Meter Verification, or SMV. SMV is the only in-situ, on-demand diagnostic system that tests the entire meter, verifying meter health, flow tube integrity, and electronics, all without having to interrupt the process. SMV ensures that the meter is operating as well as the day it left the factory. It's like having a virtual calibration stand built into every flow meter in your system. With SMV, Tom can verify his meter in 90 seconds or less. SMV cuts the cost of calibration improving because Tom can run it more often within his plant. Tom can even run SMV daily to provide a robust audit trail or use SMV to bolster measurement confidence. SMV also creates a safer work environment. It can run remotely, which is a huge advantage in harsh conditions or dangerous applications. With SMV, Tom captures the data he needs. Plus, he gets verification reports, making it easier to comply with third-party agency requirements. And he can manage his process better and reach peak efficiency. SMV delivers the measurement confidence you need at a cost that improves your productivity, all while keeping your employees safe. To learn more about SMV and micromotion Coriolis meters, visit www.micromotion.com/SMV.
I hope you enjoyed that short video on SMV. There are a number of third-party organizations that currently accept or are evaluating smart meter verification for acceptance, as you can see here in this list. One of these recognitions is by the U.S. EPA as a way to meet 40 CFR Part 98. Customers choose Coriolis here for ease of use and affordability of calibration verification. Some have saved up to $300,000 per year on reduced or eliminated calibrations. With Emerson as your measurement partner, we can help you reduce the costs associated with meeting new environmental regulations, improve plant availability, reduce energy costs, and ensure safety. We have helped many power generation customers in these areas, and we would love to help you as well. With the combination of innovative technology and field experience, we look forward to helping you improve your bottom line. I hope you have found this information valuable. I'd like to ask one last quick poll question. What is your timeline for upgrading your ammonia-related flow measurement equipment? Well, please reach out to your Emerson Flow representative for all your measurement needs. Thanks for attending this webinar. At this time, we will take a few questions. Please remember, if we don't have time to get to your questions, you can use our Contact Me form to access follow-up assistance. Thanks again.
Thanks so much, Marty, for all this great information. As Marty just mentioned, we're now going to open it up for questions. So please use the Q&A chat panel to ask the questions. And it looks like, Marty, we've already got a couple come in, so I'll hand it back to you.
Great. Yes, let's see what we have here. Can a Coriolis meter measure ammonia concentration and flow at the same time? Yes, in a liquid application, we do both measurements independently. So the answer is definitely yes. Here's another one. What outputs can I get from the meter for flow and density measurement? Flow measurement, we can provide both mass flow and volume flow. Volume flow is we use our live mass reading and our live density reading, or on a gaseous flow, we could use the density value at a standard condition to give you a volumetric gas flow. Another one here. What temperature limits do you have on the meter? The standard sensors are up to 400 F, and we have high temp versions that go up to 662 Fahrenheit. How many SMV results can be stored in the transmitter? Currently, we can store up to 20 different verification results inside our transmitter that can be downloaded at any time. Looks like that's it for now, Allison.
Okay, perfect. Well, thanks so much, Marty. As we've mentioned, if you have any future questions, please don't hesitate to reach out and contact us. You can use the Contact Us button at the bottom of the page there, or as I mentioned, we will be sending out the recording 24 hours post-webinar, and you can always also contact us via that email. So we'd like to thank you again for joining us on today's webinar and for all the great questions that we received. On behalf of our guest, Marty McDonough, as well as everyone at Emerson Micromotion, we thank you for joining us and taking the time to view the presentation, and we hope that you have a great day. Thank you.